this is the sampling distribution for proportions. So it's pretty much we are looking at the binomial setup we have seen before. So in other words, each trial with two possible choices, success or failure. The probability of success is P and the failure is 1 minus P, which is Q. So the trials, they are independent, identical trials, each trials. So in general, we want to estimate this parameter for the population, what fraction is going to be the S basically. So this P unknown parameter we want to estimate, or a function of that. So of course, if you have to estimate that, so we need to pull a random sample. So when you pull a random sample, you are looking at n trials. So the trials look like, so either your sample is going to be success or failure in out of those n things. So if I ask you, out of this is your sample, n values in there, give me the best estimate for this population proportion, you can kind of, the best intuitive estimate you can get is at the sample proportion. So how many S's in there in this sample? So the number of S in the sample divided by n. That is known as the sample proportion. So P hat. So usually in statistics there's a notation. So if you want to estimate P, so this is the population parameter. So when you put a hat there, that means that this is an estimate for that. So it's like a sigma. If you want to estimate sigma, so if you put a hat, means that this is an estimate for that. So any estimate. Okay, so like that. So it's a P hat, this is a good estimate, sample proportion. So we are going to look at the central limit theorem for this sample proportion. Actually, if you look at it, you can see that. So here the number of years divided by n is almost act like x bar actually, if you give one value for the S and 0 value for the failure. Okay, so in other words, so the central limit theorem for the sample proportion is going to go like this. Central limit theorem for the sample proportion P hat, for large n, the distribution of P hat is approximately normal with mean. So this is the mean of P hat. Okay, mean of P hat is going to be the P value, the population proportion, and the standard deviation is going to be, standard deviation of P hat is going to be the square root of P and Q divided by n. So this is the central limit theorem for the sample proportions. So this n, it's not like that in the previous case. This is got to be quite big actually. See, remember that these are kind of success and failure. So if you give 1 and 0, so it's like that. So that type of. So this is n is going to be much bigger than that. Okay. So anyway, this is the central limit theorem. So the P hat is approximately normal. This n is going to be quite big. I will tell you how big it should be. It's going to be with a centered at P, and in other words, the mean of that is going to be the P. Standard deviation of that is going to be the square root of PQ and n divided by n. So this n should be large so that that P minus 3 times square root of PQ over n. And when you calculate this interval from this value to this value, so once you calculate it, this value has to be within, so if you look at the 0 and 1, this interval has to be within that. Later, I will show you basically why this is going to be the case with later in couple of 2-3 chapters down. So you will see the reason for this 3 value over there. Okay. So eventually when n is getting bigger and bigger, this is going to be correct, because the reason is that there's an n here in the denominator. So this part is getting small and small because this n is in the denominator, and you already know that the p-value is something, always p-value is in between 0 and 1. So eventually, since this is getting small and small for large n, so this is going to be correct. So n, the condition is n must be large enough so that this interval got to be within 0 and 1. Okay, so sometimes some books give different other conditions, but later you will see that most textbooks use this condition. Okay, so with 3 sitting over there. So, and later you will see that why that is correct. Okay, so here, so the first example. So in this example, so here you are looking at a sample survey interviews, a simple random sample of 267 college women. Suppose that 70% of the college women have been on a diet within the past 12 months. So what are the mean and standard deviation of the sampling distribution for the sample of 267 women? So in other words, so for each one, is either person is on a diet, so if I label it as a success or otherwise failure, that is going to be according to that 70% is 0.7, the failure is 0.3. So this is the P and this is the Q, 1 minus P. Okay, so so you're looking at this sample size. So the P hat within that sample, the proportion of women on a diet within that sample. Okay, so according to the central limit theorem, so this is quite big, but still we need to check whether this is big enough. So it's going to be centered around, it's going to be approximately normal with the P, the mean of that is going to be P, and standard deviation is going to be square root of PQ over N. So this P equal 0.7, standard deviation, so it's 0.7 times 0.3 divided by 267, so that is going to be that. So, but to answer this part A, the mean and standard deviation, this is the answer for, so this question, the mean is that, standard deviation is going to be that. Okay, so actually it is going to be normal as well. You need this part for the next question. So the next question is pretty much the continuation of the same question. If you pull this big sample like that, so this asking, use the normal approximation, mean use this thing, this approximation to find the probability that 75% or more of the women in the sample have been on a diet. So in that sample, 75% or more have been on a diet. So if you once you calculate the p hat, sample proportion, what's the chance? 75% or more, which is that as a probability 0.75, this probability, that's what we want to figure out. So first of all, of course, you need to check whether this n is big enough. Okay, so this is a big. So here the best way to check, this is the condition I gave you. The p minus 3 times 0.7, 0.3 divided by 267. So the same interval here with the plus sign. When you calculate that, so it's going to be, this part is going to be 0.084 plus or minus, and you are going to get this interval. This interval is within 0 and 1. So n is large. Okay, so this is the same condition actually. So your book at this stage is kind of little vague on this thing, the size, sample size. But anyway, you will see that later on, a couple of chapters down the road, we are going to use this condition. Okay, so anyway, it has to be within 0 and 1. So this n is large. So here now we need to figure out this probability. So now this is a normal. Since this is greater than or equal, this equal sign really has nothing to do with that, because we are going to use a continuous curve. Okay, so this is Once you get to this point greater than or equal, this is the same because we are using that approximation, normal approximation. This is, by the way, different from that binomial distribution we were using in the previous chapter. Okay, you remember that there was a continuity error type thing, so we use that. So that is different from that. So here this, so convert this into z. So the p hat minus that 0.7, I'm using this curve now, p hat minus 0.7 divided by this value right there. In other words, actually this value is that, so that this will convert into z, and that this is going to be eventually 1.79. Read the z table to get that. So this is going to be 0.0367. Okay, so this is the probability. So the next example, so if you so this is a survey, so 2010 survey says that 13.9%, so out of this many people, million people, basically they identified themselves as Hispanic origin. So the question is that, is the value 13.9 a parameter or statistic? So the thing is that you are looking at the whole US population. So it's technically that when you take the census, you're supposed to hit everybody. Okay, so for all practical purposes, this is a parameter actually. You are supposed to take everybody. Okay, so once you get that, this supposed to be like supposed to be almost for all practical purposes. Actually, it is going to be the parameter. Okay, because we are dealing with the whole US population. You're taking the whole data. Okay, so but the second question now, so what you're looking at in this one, so you're looking at a opinion poll. Opinion poll has only 1,500 people. So out of that 1,500 people, this is the sample proportion out of that 1,500 people. So that will behave like that using that central limit theorem. This is the P and PQ over N. Okay, so this is the central limit theorem. So for this part A, so the mean for that is that, standard deviation for P hat is going to be that, basically is that. Okay, so that's the answer for part A. So the answer for part B, so you want to figure out the probability that the P hat is going to be less than 0.12. Okay, so this probability you need to figure out. So here this one is going to be, so convert into z, so this thing minus the mean divided by the standard deviation. Do the same thing here, this will turn into z, so this z less than that, so it's going to be, use the z table to figure out that probability, that is going to be that. Okay, so this is the answer. So for you to check that when this n is large, so you need to calculate this interval just like in the previous case, p minus 3 times square root of that. That interval is going to be, so this is 0.139, 3 times this part is going to be this, so 3 times that, so calculate this interval is going to be this minus that plus that, interval is that, so this is of course within 0 and 1, so that n is large. Okay, if you look at, say for example 100 value, most probably this is not correct, you may want to check that. Okay, so you are going to end up with the negative values, so it's not going to be within that, you might want to check that. Okay, all right, okay, that's about example. So next time I will go to the next chapter.